So to find the number of stereoisomers, you have to look at the number of chiral centers. The number of chiral centers is related to the number of stereoisomers by this formula here, 2 to the n. So this is going to be the number of stereoisomers, where n is the number of chiral centers. So if you have one chiral center, this means that you have two isomers, two stereoisomers in there. You are asked to find them, you're asked to draw them also. So let's have an example. Draw all the stereoisomers of lactic acid. This is lactic acid over here. I'm giving you the structure. And you need to label the configuration of their stereogenic center, of their chiral center in there. So the first thing that you would need to do is draw it and then label the chiral center. Normally it's easier to view it once you when you write it down. This is a CH, basically this is not a chiral center over here. That asterisk basically has to be moved all the way here. This is your chiral center. So normally it's easier to view once you write. So I'm having a CH3, it's going to be a CH. This is going to be an OH. I'm going to put my COOH over here, and then I do have a hydrogen. So basically this is my chiral center that has the 4 different groups around it. These are the 4 different groups around it over there. I have one chiral center, so the number of stereoisomers is 2 to the 1. N is the number of chiral centers, so I have 2 stereoisomers. Now you have to draw your isomers in there. So drawing the stereoisomers, since you have one chiral center, it's easy. Just to draw it in a tetrahedral geometry. This is the easiest thing possible. Draw it in a tetrahedral geometry. Throw in the groups anywhere you want. It doesn't matter. Just remember that this is a tetrahedral carbon, so it needs to have 2 bonds in plane, 1 bond in front and the other one is behind. If you have the possibility of choosing, make sure that always your lowest priority group is always behind. So hydrogen in this case is always behind. Locate your priorities here. So I could put the OH up there, I can put the OH in front, I can put it in plane here. It doesn't matter. It doesn't matter, so because no matter where you put it, you're gonna get one isomer, and then the mirror image is gonna be the second isomer. So it really does not matter in that case. But just make sure to stick to the rule for the drawing the tetrahedral geometry. 2 bonds in plane, 1 in front and the other one is behind. Set your priorities, please. This is 1, this is 2, this is 3. Hydrogen is behind, so basically look away from the lowest priority group. I'm going by 1, 2 and 3, and this is counterclockwise. It's an S configuration. Draw the mirror image. Whatever you see on this side is the first thing that you see on the other side. The OH stays in plane, it's up there, and then the acid stays in front, but now it's on the other side, and then the hydrogen stays behind and it's on the other side. If you get one isomer with a certain configuration, then your second enantiomer needs to have an opposite configuration. It has to be an opposite configuration because one of them is rotated around the chiral center to the right or left, and the other one is rotated in the opposite direction. So these are basically my 2 stereoisomers. We say that the 2 stereoisomers here are a pair of enantiomers. Okay. Now drawing Fisher projection. This is a method that normally we use in order to draw one or more chiral centers. So if you have more than one chiral center, it's easy to represent it rather than drawing the 3D structure like that as a tetrahedral structure. Normally we draw it in a form of a Fisher projection. Now what is that? A Fisher projection is basically represented like a cross, and the vertical line basically means that the atoms or the molecules on it, they are behind, and the horizontal line means that the molecules on it are in front. If you have a molecular model, you can easily view it. You can easily view it, seeing the acid and the CH3, basically they are behind, and the hydrogen and the OH popping out, and this is going to be in front. We're still having the tetrahedral geometry in this case, but this is the representation in the Fisher projection. So any group that lies on the horizontal line, this means that this is in front. And normally what we do when we draw, when we transfer a molecule into its Fisher projection, we always make sure that the carbon chain is always on the vertical line. See the carbon chain? Always on the vertical line. The highest oxidized carbon is always on top. So this is an acid. It's the highest oxidized carbon. It's always on top. So the acid is always on top and there. And then hydrogen is always in front. And when we do the configuration, simply we reverse it. I'll show you how. So this is how we draw it. Carbon chain is always on the vertical line. The highest oxidized carbon is always on the top. And then hydrogen is always in front in Fisher projection. By drawing the Fisher projection, you don't need molecular models anymore, and you don't need to swap anything. Okay? So here what I have, if I want to draw, or if I want to find the configuration around this chiral center, you set your priorities. I have a CO, so this is going to be 1. I have a CCO, this is going to be 2. And then I'm having a CC, this is going to be 3. And I'm going by 1, 2, and 3. See how am I going? I'm going clockwise. This is an R, but see, hydrogen is in the front. It has to be behind. So simply invert the configuration. So instead of being R now, it's going to be S configuration. Notice I did this without even swapping and without having any molecular models in there, without doing anything, no rotation, nothing. So keep the hydrogen in front, figure out your configuration, and then reverse it. And in this case, it's going to be an S instead of an R. There are rules for the Fisher projection. As we said, the carbon chain is always on the vertical line. Fisher projections are represented in forms of horizontal bonds and vertical bonds. The horizontal bonds, these are the bonds that are pointing up with respect to the plane of the paper, so they are in front. The vertical bonds, these are pointing down with respect to the plane of the paper, so they are behind. The highest oxidized carbon is always on the top. You guys, always when you do the rotation always is going to be in a plane. And when you do the rotation, always rotate 180 degrees every time. Don't rotate 90, because if you rotate 90, you change the molecule. Rotation 90 degree, you get the mirror image. Pay attention to that. Rotation of 180 degrees does not change the molecule. So rotation 180 in plane does not change the molecule. If you rotate 90 degree, you will get the mirror image. It's as if you are swapping. So you get the mirror image. Do not rotate out of plane. Always rotation has to be around the horizontal axis. So let's have an example in here. So we are having this molecule, okay? In Fisher projection, see the carbon chain is on the vertical line. Hydrogen is in the front, the highest oxidized carbon on the top, and then do your configuration in there. So I'm going by 1, 2, and 3. Hydrogen is in front. I just neglect the hydrogen. Neglect it. Go 1, 2, 3. This is counterclockwise. It's an S. But since hydrogen is in front, I invert the configuration, and now it's an R configuration. Here I'm going by 1, 2, and 3. This is going to be an R configuration. Hydrogen is in front, inverted, and this is an S configuration. Always do the rotation around the horizontal axis. So your rotation here in this case is going to be 1, 2, and 3 around the horizontal axis. This is going to be 1, 2, and 3. This is your rotation in that case. One more thing. When you draw the mirror image of Fisher projection, notice that the vertical line stayed the same in the mirror image. It didn't change. But the horizontal line is the rotation. This is the rotation around the horizontal axis. So I am rotating around the horizontal axis 180 degrees in this case. Okay, so you're rotating in this case, so the hydrogen becomes here, basically your OH becomes here. This is the first thing that you see. The hydrogen is there, so all what I did is just I rotated. This is what I did. I rotated 180 degrees. I didn't swap. I didn't, because if you swap this group with this group, this is your rotation of 90 degrees. Pay attention to that. You change the molecule. But if you rotate 180 degrees, here in this case, you basically what you did here is you ended up getting the enantiomer in that case. But if you swap, then you change the molecule in that case. So we said that Fisher projection normally comes in handy whenever you have more than one chiral center. So here I want to draw all the stereoisomers of 2-bromo, 3-chlorobutane. The 2-bromo, 3-chlorobutane, they do have 2 chiral centers. So the number of stereoisomers is 2 to the 2, so it's going to be 4 stereoisomers. Now I have to draw them all. To draw them all, the first thing that I need to do is convert this structure here into a Fisher projection. Every cross, when the horizontal and the vertical line meet, that is going to be a carbon. And in our case, the carbon is going to be a chiral carbon. So basically here I'm having 2 chiral centers. I'm having chiral center 2 and chiral center 3 in that case, numbering from the side. So numbering from this side, since B is the lowest in alphabetical order, so I'm starting over here. This is carbon number 2. Carbon number 2 is connected to a CH3. This is my carbon chain. This is my carbon chain along the vertical line. So carbon 2 is connected to carbon 3. Hydrogen and the bromine. So the hydrogen and the bromine, I'm just going to put them along the horizontal line. And then carbon 2 is connected to carbon 3. This is carbon 3 over there. And then carbon 3 is connected to a CH3, and then a hydrogen and a chlorine. You can put the hydrogens and the bromines anywhere you want. So I could put the hydrogen here, the bromine there. I could put the hydrogen here, the chlorine there. It does not matter, because wherever you put the hydrogens and the bromines, you're gonna basically get your second stereoisomer in there. So it really doesn't matter. You're gonna get all the isomers that you have for this structure. So the moment, this is the first stereoisomer. So now we're gonna go ahead. We know that stereoisomer has 2 chiral centers, right? So it's gonna have a mirror image. It will have a mirror image. If it has a chiral center, this means that it is going to have a mirror image. It is going to be optically active. It's capable of rotating the plane of polarized light. So it's gonna have a mirror image in there. For the mirror image, whatever you see on this side, you're simply gonna write it on the other side, okay? So this is going to be the mirror image. You only change the orientation. This is the 180 degrees. You only change the orientation of the horizontal lines, not the vertical. The vertical stays the same. So this is going to be the second stereoisomer. So far I did 2 stereoisomers. I need to do 2 more because I have a total of 4 stereoisomers. So in this case, what I need to do is I need to fix one carbon, rotate the other. So you look at stereoisomer B, because this is where we reached. Fix one chiral center. It doesn't matter which one. So here I fixed the top chiral center. So that chiral center, I fixed it. And I rotated the chiral center at the bottom. Now rotation of the chiral center, remember what I said. Rotate 180 degrees, please. Don't rotate 90. So you don't swap the chlorine with the CH3. You just rotate the chlorine and the hydrogen. So just rotate that. So the hydrogen becomes here, the chlorine becomes there, period. This is your rotation. hydrogen and the chlorine. And once you rotate, then you go ahead and get the mirror image for that rotation, and that will be your second pair of enantiomers. So A and B are going to be mirror images of each other. These are pair of enantiomers. C and D are going to be mirror images of each other. This is your second pair of enantiomers. So you have a total of 1, 2, 3, and 4 stereoisomers. You have basically two pairs of enantiomers. Now, to label the configuration around the chiral center in Fisher projection, you simply look at your chiral center and see the groups that are connected to the chiral center. So, for example, for that chiral center is connected to a bromine, is connected to a carbon. See, I'm highlighting the carbon. I didn't highlight the whole CH3. It's connected to a hydrogen and it's connected to this carbon. Now I know between bromine, 2 carbons, and the hydrogen, bromine is the highest priority, so bromine is going to be priority number 1. These 2 carbons in there are a tie, so I have to look at the second atom that is connected to the carbon. This is carbon hydrogen, this is carbon chlorine. Then carbon chlorine is going to be the second highest priority. So this whole thing, let's highlight that. This whole thing, the whole thing here, because we're considering this chiral center, this whole thing is going to be the second priority set. So that whole thing is going to be priority number 2, and then priority number 3 in here, and then priority number 4. So I'm going by 1, see 1, 2 is here, this is the 2, all of that is 2. So I'm going by 1, 2, and 3 like that. This is 1, 2, and 3. This is a clockwise, but hydrogen is in front, so you invert the configuration, it will become an S configuration. Clockwise is R, but since hydrogen is in front, it will become an S configuration. We're going to do the same thing. We're going to do the same thing for the second stereoisomer here. So see, or the second chiral center. So see that chiral center, it's connected to priority 1, which is the chlorine, and then this is a carbon, carbon. So this is a tie, carbon, hydrogen, carbon, bromine. So this is going to be priority number 2. The whole thing is going to be priority number 2. Then I am having priority number 3 and priority number 4. So for that chiral center, I'm going by 1, 2, and 3. Neglect 4, okay? Because 4 is, you're passing through 4. Because at the end, you're going to invert your configuration. So I'm doing 1, 2, and 3 over there, passing through 4 without considering it. So 1, 2, 3, this is basically an S configuration, counterclockwise. But since hydrogen is in front, you reverse, and that is an R configuration. The moment you find your configurations for the first enantiomer or the first stereoisomer, this is enough. You can guess all the rest. So since A and B are enantiomers, then the configurations are going to be opposite. So if this one is an S, then this is going to be an R. If this chiral center is an R, then that chiral center is going to be an S. Just guess it. It's way easier. It will save you a lot of time. Now for B and C, I know that I did nothing to the configuration of this carbon because I fixed that carbon over here. We said fix carbon, rotate another carbon to get the third isomer. So I fixed this chiral center, so that chiral center stayed R. But I rotated that chiral center over here 180 degrees. So I went from S to R, okay? So you rotated that, so this means that you went from S to R. And then the mirror image, the R becomes S and the R becomes S over here. These are the two pair of enantiomers for stereoisomers. Now let's define the term diastereoisomer. We know that A and B are pair of enantiomers. C and D are pair of enantiomers. But what about BC? What about AD? What about BD? What about AC? What are those? Those differ in one chiral center, not in both. Enantiomers have to differ in both chiral centers. So see, both chiral centers are different in configuration. Diastereoisomers, on the other end, they differ in at least one chiral center, at least one chiral center. Here in this case, because it's a total of two chiral centers, it has to differ in one chiral center. But if you had the three chiral centers, normally diastereoisomers differ in one or two chiral centers, not in all. If they differ in all chiral centers, then this is an enantiomer. If they differ in some of the chiral centers, then this is a diastereoisomer. So all of those are considered to be diastereoisomers. Diastereoisomers are stereoisomers that are not mirror images of each other. So BC are not mirror image. They only differ in one chiral center. Same thing for AC, BD, and AD. All of those differ in one chiral center. Now, let's say, for example, if you have a compound, now, as I said, if you have two chiral centers, you guys, it's so easy to draw the Fisher projection to figure out the number of stereoisomers in there in the configuration. But let's say, for example, as in some of your problems in there, they're not using the Fisher projection. They're asking you simply to draw the stereoisomer of compound using the 3D representation. How are you going to do this? So let us consider how to draw same idea as this problem over here. Same idea. I want to draw all the stereoisomers, but I don't want to use the Fisher projection. I want to use the 3D method in there. In 3D geometry in order to draw all the stereoisomers. I have the 2,3-dibromopentane. So this is basically my pentane. This is carbon 2, this is carbon 3. I have a bromine in there. Now remember, around a carbon single bond carbon, there is basically no cis and trans. Around the carbon single bond carbon, there is a free rotation. There is a conformation of free rotation. So there is no cis and trans. So I cannot name this as cis. The bromines are on the same side, yes, but this is not cis because there is a rotation around the carbon single bond carbon. So if it's cis now, it can rotate and become trans again. So this is why it's neither cis nor trans. Let's go ahead and draw the 2,3-dibromopentane and figure out how many chiral centers we have. Drawing them is, since they didn't tell me the configuration, you can put the hydrogens in front, you can put the bromine behind, but normally I prefer, if you are always given the choice, make sure that your lowest priority group is behind, and make sure that the carbon chain is always in a plane. This is why I didn't take that CH3 and put it in front, because I want it to be in plane with the rest of the carbon chain. That left me with one choice and one choice only. Since I need my hydrogen to be behind, the bromine has to be in front, and I don't have any other option with that. So this is going to be my, I have two two chiral centers, stereogenic centers. So the number of stereoisomers is going to be 2 to the n. It's going to be 2 to the 2. So I'm going to end up having 4 stereoisomers. Now I want to draw these 4 stereoisomers. To draw them, draw your groups in the tetrahedral geometry, and then do the mirror image. Since I have a chiral centers in there, then I'm going to end up having a mirror image. I have 2 chiral centers, then I'm going to end up having a mirror image in there. So the first thing that I see on the side, simply mimic it on the other side. This is the first thing that you're going to see on the other side. Hydrogen is behind, bromine is in front. Okay, and then of course, the rest of the molecule. Right now I have a pair of enantiomers. These are my 2 stereoisomers. So I drew my 2 stereoisomers. I still have 2 more. So as I did in the Fisher projection, you fix one carbon, you rotate the other. But before that, I just want to say one thing here. If you rotate 180, rotation 180, after drawing the compound, we want to make sure that simply A and B, they they don't align. So we want to make sure that A and B are not the same. They don't align and they shouldn't be the same. But this is just a test normally that we do to make sure once we draw the enantiomers in a 3D geometry, normally what we do over here is rotate the B enantiomer 180 degrees and put it on top of A and see if the bonds align. If they do not align, then we say that A and B are enantiomers of each other. They are basically different compounds and they are enantiomers of each other. In this case, they definitely they don't align because I have two chiral centers in there, so they don't align. So A and B are non-superimposable. This means that they are mirror images. Again, in order to check whenever you draw your 3D geometry there, if you want to check your enantiomers if they align or not, all what you need to do is simply rotate 180 degrees, take A, put it on top of B, or take B, put it on top of A, and see if the bonds align. If they don't align, then we say that A and B are pair of enantiomers. This test is normally important every time you are figuring out the enantiomers. The enantiomers in there, rotate 180 and then put them on top of each other and see if they align or not. Now, for the second two stereoisomers, because remember we had four. For the second two stereoisomers, so here's what we're gonna do. Remember what we said, that once you switch groups, in there, you get the other pair of enantiomer. Okay, so we're gonna switch over here the bromine and the hydrogen. So I'm keeping everything and I'm swapping the hydrogen and the bromine. It's the same idea as I did over here, and I rotated. It's the same idea, fixing one carbon, rotating the other carbon 180 degrees. It's exactly the same idea. So here what I did is simply I swapped the hydrogen with the bromine, and by swapping the hydrogen with the bromine I get another structure, now a completely different structure, and that structure I'm going to draw its mirror image. So that is going to be the mirror image for it, and now I'm going to get my basically my pair of enantiomers. So if you take that now and rotate it 180 degrees and put it on top of D, they shouldn't align at all. They shouldn't align, so this means that C and D are another pair of stereoisomers. So by doing this, I ended up having a pair of enantiomers, and then C and D another pair of enantiomers. So I'm ending up having two pairs of enantiomers. These are my four stereoisomers. Having also A and C, B and C, B and C, B and D, and A and D, all of those are considered to be distereoisomers because they differ in one chiral center in this case. They don't differ in all the chiral carbons, they differ in one chiral center. Okay, let's do the same example using the Fisher projection. It's way easier. When you're doing the Fisher projection over there, do the number of stereoisomers and then go ahead and change it into a Fisher projection. Now, once you change it into a Fisher projection over there, notice the groups are different, and we're going to talk about these groups in a second over there. So the groups are different. We know that we have two chiral centers. This is 1 and this is 2. Draw the mirror image for. Fix one carbon. I fixed the carbon on the top here, and I rotated this carbon along the axis 180 degrees. So the hydrogen became here and the bromine became there, and then get the mirror image for, and these are going to be my four stereoisomers in that case. Another example, so to define distereoisomers, these are not mirror images, so they should differ by one chiral center. So see, carbon 3 is S configuration here, and it's R configuration there. So they differ in one chiral center. Chiral center 2 stays the same. Chiral center 3 is different. So this means that the two molecules are diastereoisomers of each other. When you're setting the priority again, you look at one atom at a time. So with respect to this chiral center here, this is a priority 1. This you have a carbon, oxygen, carbon, bromine. Notice, carbon, don't let this basically confuse you. You have a carbon, oxygen, carbon, okay, you have a carbon, bromine, you have a carbon, oxygen. So that is going to be 2, and that is going to be 3. And I'm going by 1, 2, and 3 on carbon number 2 like that. So that is going to be, hydrogen is behind, that is going to be an S configuration. Okay? Here, I am going by priority 1. Let's change the color. I'm going by priority 1 on this carbon. On that side here, this is going to be carbon, this is going to be a 1 carbon, it's going to be carbon, carbon, oxygen. So this is definitely the second, this is the third, and this is the fourth. And I'm going by 1, 2, 3 again like that. This is basically an S configuration. Hydrogen is behind, stays behind, so it stays in S. Whenever I'm finding the configuration, I want to make sure that hydrogen is behind. And if it is behind, don't do anything. Keep the configuration the same. Now, when hydrogen is in front, what do I need to do? If you have your molecular model, please rotate. Make sure that hydrogen is at the back. If you don't have your molecular model, what we're going to do is we're going to take this hydrogen and we're going to swap it with this bromine. So now this hydrogen becomes a bromine, and this bromine becomes a hydrogen. So this is going to be priority 1 here, priority 2, and the priority 3. Whatever configuration you're going to get, that is going to be for the enantiomer. So you have to reverse that. So it's going to be 1, 2, and 3. See, this is going to be an S configuration on carbon 3. That S configuration is for the enantiomer. You remember, you swapped. So this is for the enantiomer. So this is why I have to reverse it. So now it is an R configuration on 3. And this is why I have it as an R configuration over there. So diastereoisomers, they are not mirror images of each other. And normally they occur with molecules with more than one chiral center. Because if you have one chiral center, then the molecule is going to have a mirror image, and that's it. Diastereoisomers start to form whenever you have the possibility of a second chiral center. So now you can do a rotation, you can rotate and get the diastereoisomer. A special form of diastereoisomer that contains no stereogenic center at all is the cis and trans. The cis and trans, these are called the geometrical isomers, and these are not mirror images. Now, so far we studied cis and trans with cycles. So if you have a cycle, if you have two substituents on the cycle, no matter where these substituents are on the cycle, the substituents can either be on opposite sides or they can be on the same side. And we said that these substituents are normally, they show stereochemistry, and the stereochemistry is in a form of a geometrical stereoisomer. It's going to be the trans and the cis. Now, there's another way that you can use the cis and trans, and that exists between double bonds. But right now here, you don't have any chiral center. Here, you do have a chiral center, but here you don't have a chiral center. Here, both are chiral centers, okay? But here, there are no chiral centers because you have an sp2 hybridized carbon. Both are considered to be diastereoisomers. This one is considered to be a diastereoisomer, a form of geometrical isomers, because there is no chiral center in there. Now let's explain the term meso. What is meso? Meso is whenever you have two chiral centers in there. Let's fix that. Okay. So meso is whenever you have two chiral centers, so this is the example, whenever you have two chiral centers and you have groups that are the same. So you have chiral centers, more than one chiral center, and you have groups that are the same. So see, I have a bromine, bromine on both chiral centers. I have a CH3, I have a CH3. I have a hydrogen, I have a hydrogen. So you should have groups that are the same on both chiral centers in there. And you should be able to draw a plane of symmetry, an internal plane of symmetry that cuts the molecule in half, something like this. So take a look here. Between those two chiral centers, I can draw a plane of symmetry that cuts the molecule in half. Now that plane of symmetry is going to bisect the molecule around the CC bond, cutting the molecule in half in a way that one is the mirror image of the other. See, one part is the mirror image of the other. So in that case, and in that case only, no need for me, there is no need for me to have a mirror image, because there is no mirror image. The molecule has a mirror image within itself. So if I want to draw the mirror image of this molecule here, the mirror image, if I rotate it, the bonds, if I rotate it 180 degrees, the bonds are going to align with each other. And if they align with each other, this means that the molecule and its mirror image are identical. They are the same. So normally meso compound, they do not have mirror images, because you can draw a plane of symmetry within the molecule, and you cut the molecule into two parts. One part is the mirror image of the other. So no need for you to draw a mirror, because if you draw a mirror image, that image, if you rotate it 180 and put it on top of this one, they are gonna align with each other. Let's consider these two cases over here. With this problem, with this structure over there, I do have bromines in opposite planes. I have CH3s in opposite planes. So there's no way for me I can draw a plane of symmetry, because drawing a plane of symmetry is not gonna cut the molecule into two parts that are basically aligning with each other. Since the bromines are in opposite planes and the CH3s are in opposite planes. So that structure here has a mirror image, and its mirror image basically is this. So this is going to be the mirror image 4. Okay, so yeah, there is no plane of symmetry. The molecule exists as a pair of enantiomer. So this is its enantiomer over there, and we say that the molecule is chiral. We define that a chiral molecule is a molecule that has a mirror image. An optically active molecule is a chiral molecule. To determine if the molecule is optically active, you have to put it through the polarimeter. So this is going to be an experiment in the lab. But normally all chiral molecules are optically active. So all chiral molecules are optically active. And for a molecule to be chiral, it has to have a mirror image. Has to have a mirror image. To have a mirror image, I should not be able to draw a plane of symmetry through the molecule. Here, I am able to draw a plane of symmetry through the molecule. So if I am able to draw a plane of symmetry through the molecule and cut the molecule into two parts, if I draw a mirror image for it, the mirror image is going to be exactly the mirror image. So see here, I'm drawing a mirror. So here you go. If I draw a mirror image here for the molecule, the mirror image is going to be the same as the molecule itself. So these two are identical. They are identical. So no need for me to draw a plane of symmetry. So I would say that this molecule here exists as a meso compound. So I have a pair of enantiomers, and then I have a meso compound. When you want to figure out your plane of symmetry, you can draw your plane of symmetry along whatever axis you choose. There is no direction for the plane of symmetry. So see that molecule in here? That molecule, I can draw the plane of symmetry vertical, I can draw it horizontal. It doesn't matter. Either ways, I am cutting the molecule in half, so basically this part is going to align with that part. Okay, so and or this part over here is going to align with that part over there. So so I would say that even though I have, see how many chiral centers you have. Okay, I have a chiral center here, I have a chiral center there, I have a chiral center in here, and I have a chiral center in there, because each one of those have four different groups around it. A hydrogen, a CH3, all this group and all this group, and all of them are different. So I have four chiral centers. But since I am able to draw a plane of symmetry that cuts the molecule in half, then I would say that the molecule is not chiral. So this brings us to at the beginning of the chapter, when we said that if you have one chiral center, the molecule is chiral. It has a mirror image. But if you have more than one chiral center, then the molecule may or may not be chiral. It may not be chiral if you are able to draw a plane of symmetry. If you are able to draw a plane of symmetry, then the molecule does not exist in a form of an enantiomer. There is no mirror image for it, as in this one. So even though I have chiral centers are not a definition for a chiral molecule. These are two separate things. A chiral center is a center with four different groups. A chiral molecule is a molecule that has a mirror image. This guy here doesn't have a mirror image because I am able to draw a plane of symmetry within the molecule. Same thing, I am able to draw a plane of symmetry within the molecule in there that cuts the molecule in half. Normally, it's easy to view it if you draw the molecular model for it. So if you have your molecular model kit, draw the molecular model for this one and try to imagine drawing a plane of symmetry. You're going to see that the plane of symmetry is going to cut the molecule in half, so that this part and this part, they're going to align with each other, as you can see. So once I have this, see, even though I have four chiral centers in there, see the four chiral centers? These are my four chiral centers. My molecule is not going to be chiral. On the other hand, if I have a Fischer projection, remember what we said about, so all of those, this is going to be a meso compound, this is going to be a meso compound, and that guy over here is going to be a meso compound. So a definition for the meso, you should have groups that are the same, because at the end you're aligning them together. You're just folding this half on top of this half. So you're aligning them. You're seeing if they are superimposable. If they are superimposable, then the molecule is not going to be chiral. It's going to be optically inactive. So over here, this is a chlorine, groups are the same, groups are the same, groups are the same. I can simply draw a plane of symmetry through the molecule, so this part is going to align with that part. It's as if I am drawing a mirror image within the molecule itself. So I would say that this molecule will have no mirror image at all, because if it has a mirror image, if I rotate the mirror image and I align, so rotation 180 degrees and aligning it, you're going to end up getting the same molecule. Let's have an example here. So I have a molecule here with two chiral centers. So let's see, if I draw the mirror image for it, I know that I can draw a mirror, a plane of symmetry. So I know from here, since I'm able to draw a plane of symmetry, there is no mirror image at all. Because whatever I'm going to draw, if I rotate 180, that is going to be exactly that same molecule there. So this is why I am testing. If I draw a mirror here, what's going to happen? So drawing a mirror image of this molecule there, if you rotate 180, you're going to end up getting this guy here. So you're going to end up these two being identical of each other. So these two are identical. They are the same. So these two are going to be the same. So no need for you to draw the mirror image for, because they are the same. So you would say that this exists as a one meso compound. Okay? So let's have an example. Consider the molecule with two equivalently substituted chirality centers, okay, such as 2-butanediol. So I'm giving you the 2-butanediol. This is the 2-butanediol over there. You have an OH here, you have an OH there. And the question is, write down all the stereoisomers. So to write down all the stereoisomers, you have to check how many chiral centers you have. I have two chiral centers, so the number of stereoisomers is equal to 4. Now, normally the number that you get here, that is going to be the maximum number of stereoisomers possible. You might get less, but you're not going to get more. So let's figure out how many chiral centers we can draw. I know that the maximum chiral centers I can draw is 4. So you're going to change this guy over here. So let's go ahead and draw it like that. So we're going to change it into a Fisher projection. I normally prefer Fisher projection rather than the 3D geometry when figuring out the number of stereoisomers in the configuration. Unless, of course, you are asked to draw it in a 3D geometry. So I'm changing this guy over here. So let's just start with this carbon here. Okay, so with this carbon in here, what I have is, again, your carbon chain has to be on the vertical line, and then the only thing that is left is the OH and the hydrogen. So you have your OH and you have your hydrogen over there. Hydrogens always be in front. You can put your hydrogen on this side, you can put it on the other side. It really doesn't matter, because wherever you're gonna put it, you're gonna do the rotation, so you're gonna get the second isomer. And do the same thing for the second chiral center over there. So this is gonna be my two chiral centers. Okay, so once I have my two chiral centers in there, go ahead and figure out the mirror image for when you draw the mirror image for Fisher. As I mentioned, keep the vertical line the same, rotate the horizontal lines 180 degrees. So you rotation the horizontal lines and you're going to get the second pair of enantiomers. So these two are going to be enantiomers of each other. If I want to figure out the configuration, that is going to be group 1. This whole thing is going to be group 2, because I have a CO versus a CH. So this is going to be 2, this is going to be 3. So I'm going by 1, 2, and 3 like that. See, this is an S configuration, but hydrogen is in front, though I'm going to reverse it and it will be an R. Here I'm going by 1, 2, and 3. I'm doing the same thing. It's an S, hydrogen in front, reverse it, that is going to be an R. Once I figure out the configuration of one pair of enantiomer, then it's easy for its mirror image. If this is RR, then the mirror image is SS. Now to figure out the second two stereoisomers, since we had a total of 4, 2 to the n, so 2 to the 2, this is a 4. So to figure out the second pair of stereoisomers, all what you need to do is simply fix one carbon, rotate the other. Doesn't matter which carbon you fix, again. So I'm fixing the one at the top apparently here and rotating the one at the bottom. So when you rotate 180 degrees, 180 degrees. You don't do 90. If you do 90, you get a completely different structure though. So you do 180 degrees. So when doing 180 degrees over there, that is going to be our diastereoisomer. So between these two, they differ in one chiral center, which is this one over here. So these are my diastereoisomers. Now all what you need to do is just figure out its mirror image. But because now you're here, you need to stop. You need to stop and see. I have all the groups the same. I have OHs the same. I have CH3s the same. Let's use another color in here. So I have the CH3s, they are the same. And then I have my hydrogens that are the same. This is the definition of a meso compound. Meso compound is a compound where all the groups are basically the same on the chiral centers, and you are able to draw a plane of symmetry, an imaginary plane here that cuts the molecule in half. So if you are able to draw a plane of symmetry, then your molecule is going to be achiral. And if it's going to be achiral, it's going to be optically inactive. So there will be no mirror image. Because if you drew the mirror image, that image, if you rotate 180, it's going to be exactly the same as this molecule over there. So there is no mirror image, so we say that this molecule exists as a form of one meso compound. So notice in reality how many stereoisomers you figured out. You figured out a pair of enantiomers, so the number of stereoisomers are a pair of enantiomer plus one meso compound. At the beginning here, we said that the number of stereoisomers is 4, but in reality, it's a 3. It's less than that because we have a one meso compound with no mirror image. Let's have another example. Draw all stereoisomers of tartaric acid. So you draw tartaric acid. Normally I give you the structure of tartaric acid, and tartaric acid is this. You do have your acid here. So this is going to be your acid. This is going to be your OH. This is going to be your OH, and this is going to be your acid. So this is what a tartaric acid looks like. It's a chain of 4 carbons. This is your 4 carbons over there, including the carbon of the carbonyl. So 1, 2, 3, and 4. And it does have 2 chiral centers. This is the first chiral center, and this is the second chiral center over there. So the number of stereoisomers is 2 to the 2. It is 4. That is the maximum number of stereoisomers. But notice, I have basically groups that are the same in here, so I can simply draw a plane of symmetry in here, cutting the molecule in half. So this is an indication that here you go, I have my meso compound over there. So draw your molecule. Then you have A and B are pair of enantiomers, so these two are pair of enantiomers. Now fix one carbon. Here I'm fixing the one at the bottom. So the one at the bottom I'm fixing, and I'm rotating the one at the top 180 degrees. So this is the one at the top over there, rotated. Now if I do this, wait, you need to pay attention. The groups are the same. They are aligning with each other. See, all of them are the same. I can simply draw a plane of symmetry. So the molecule does not have a mirror image. See whatever I drew in here? Just to tell you that this guy is the same as this guy. If I rotate 180 along this axis, if I rotate 180 and put it on top of this compound, then these two are going to align with each other. So no need for you to show this in the first place, because these two are identical with respect to each other. So you would say that the molecule exists in a form of a pair of enantiomers and a meso compound. I will explain racemic mixture as I proceed, and I'm going to come back to this slide, okay? So let's have more examples now. We have cyclic compounds. So how many stereoisomers for 1,2-cyclopentane diol? Cyclopentane diol is this. I did not specify. Remember, when we have cycles that have 2 substituents on them, then you're going to end up having the cis and the trans. So I didn't specify cis and trans, so you have to consider both. We're going to consider the cis first in this example, and then we're going to consider the trans. I know that 1,2-cyclopentane diol, this is it, has how many chiral centers? How many chiral centers does it have? See, it has 4 chiral centers because I do have a hydrogen in here. So this is 1, 2, 3, and 4 groups, 4 different groups. So this is going to be a chiral center, and that carbon over there is going to be a chiral center. It has 2 chiral centers. So the total number of stereoisomers is going to be 4. 2 to the 2, so it's going to be 4 stereoisomers. I have to draw them. So to draw them, notice here, I cannot use Fisher, because Fisher is for alkane chains. They're going to say it again. Fisher is for alkane chains. So I cannot draw Fisher. With cycles, I only have to draw the cis and the trans for the substituents. So I have 4 stereoisomers. I'm going to start with the cis substituent and see if it has enantiomers. And then I'm going to do the trans substituent and see it has a mirror image or a pair of enantiomers, exists as a pair of enantiomer. So with the cis, I can simply draw a plane of symmetry along this carbon, see? Can draw a plane of symmetry, cut that molecule in half. So this guy over here does not have a mirror image, it's within itself. So it is going to be a meso compound. Again, groups are the same, everything is the same. The two halves, basically they align with each other, they can fold with each other there. So I would say that the cis exists as a meso compound. The trans now, for the trans, I cannot draw a plane of symmetry because the OHs are in opposite planes. If I do, I won't have the two sides basically aligning with each other. So the trans will have a mirror image in this case, and it will exist as a pair of enantiomers. So it will have a mirror image, and that is going to be the mirror image. Notice, the mirror image of the trans is a trans. The mirror image of the cis is cis. If I have cis and trans and I want to compare them, these are diastereoisomers. These are not enantiomers. Enantiomers means that the mirror image of cis remains cis, the mirror image of trans remains trans. Pay attention to that. So now instead of 4 stereoisomers, I have 3. I have a pair of enantiomers and the meso compound. How many stereoisomers for 1,3-cyclohexane diol? So this is going to be the cyclohexane diol. It's up to you. You can draw it in a chair conformation, or you can draw it as a planar. It's fine by me. I didn't specify because I want you to draw both the cis and the trans. I have 2 chiral centers, so the number of stereoisomers is 4. 4 stereoisomers going to be the cis and the trans. So you consider the cis alone and then the trans alone. You could have made the CH3 and the OH to the top though, in front, but here I made them behind. They are the same. So so having the CH3 and the OH here behind, can I draw a plane of symmetry? No, because the OH and the CH3s are different. I cannot draw a plane of symmetry. So if you cannot draw a plane of symmetry and you have a chiral center, immediately you have a mirror image. So cis exists as a pair of enantiomers. Trans also exists as a pair of enantiomers. So these are your 1, 2, 3, 4 stereoisomers. Okay? As I mentioned, very important, when you draw a chair conformation and you want to draw its mirror image, equatorials stay equatorials. Equatorials stay equatorials. Axials stay axials. So whatever is up stays up. Whatever is down stays down. Good? Okay, so again, whatever is up stays up. Whatever is down stays down. If you have cis substituents, their mirror image has to be cis. So this is down, down. This is cis. That is going to be down, down, and this is again cis. So cis has a cis mirror image. Trans, this is up, down, trans. Trans has a trans mirror image. Let's have another example over here. The 1,3-dibromocyclopentane. I'm giving you a lot of examples, and notice all of these are cycles, so I did not change that into Fisher because I cannot. I only have to consider the cis and the trans isomers in there to determine the total number of stereoisomers or stereogenic centers. So I have 2 chiral centers in there. Total number of stereoisomers based on the stereogenic center. It's related because the total number of stereoisomers is 2 to the number of chiral centers. So here it's 2 to the n, 2 to the 2, so it's 4 stereoisomers. You have to consider the cis, you have to consider the trans. Notice the cis here, I can draw a plane of symmetry. So the cis will exist as a form of isomer, it will exist as a meso compound. On the other hand, the trans No, the trans, I cannot draw a plane of symmetry because the bромines are in opposite planes. So that guy over here will have a mirror image. So we're starting with the cis. The cis can have a mirror or a plane of symmetry passing through this carbon. So you don't have to draw its mirror image, because the mirror image, if you rotate 180, it's going to be exactly the same as this molecule. These two are going to be identical with respect to each other. So cis isomer exists as a meso compound. Meso compounds are not chiral. They are achiral molecules. The trans, on the other hand, it does exist as a pair of enantiomers. So the total number of enantiomers, or the total number of stereoisomers, is going to be a pair of enantiomers and one meso compound.